to our today's lesson, and today I want to actually focus on the second method of preparing or coming up with sodium carbonate, which is also referred to as soda ash or washing soda. In the last lesson or discussion we had, I had actually tried to explain how soda ash or washing soda can get obtained by what we refer to as extraction from Lake Magadi, or maximizing on the use of fractional crystallization, where the difference in solubility of trona and sodium chloride or concentrated sodium chloride or brine can get separated on the basis of fractional crystallization. That is to say, the difference they have in as far as solubility is concerned in water at a particular temperature makes it possible for them to get separated. So today we shall discuss how the same end product, a compound of carbon called sodium carbonate, can get obtained through a process referred to as Solvay process that gets carried out on an industrial scale. So we have sodium carbonate that I'm as well referring to as washing soda, or also referred to as soda ash. So apart from it getting obtained from Lake Magadi, from a main raw material referred to as trona or sodium carbonate, sodium hydrogen carbonate, and two molecules of water of crystallization, the same trona can be able to give us again what we call sodium chloride. Where is sodium chloride located? The sodium chloride gets trapped between the molecules of water of crystallization. In that process, when crystallization actually gets carried out at a very low temperature at night, the sodium chloride crystallizes out. It is able to undergo what we call purification, crushing. After it has been dug using what we call bagged dredges, and then it actually gets bagged before it gets transported to the market. We always know that sodium chloride is actually used in food seasoning and as a meal for animals. It can also actually serve as a source of sodium metal when electrolysis gets carried out in what we call a down cell. Okay, so I think let's go to the second way of obtaining sodium carbonate or trona component. And in this case, we are going to look at how a process called Solvay process, of course, it actually got brought into existence by a particular scientist called Solvay, and he actually outlined how sodium carbonate can get to that point of being manufactured in as far as the setup we came up is concerned. And in this case, he actually brought into existence a particular setup that he came up with that can help us to actually come up with the manufacturing of sodium carbonate. So a diagrammatic representation, a flow chart that can summarize the Solvay process that aims at manufacturing sodium carbonate can be as follows. And I'm going to use that flow chart or diagrammatic representation to be able to explain how this process ends up manufacturing sodium carbonate, which is required on industrial scale and on commercial scale for different purposes. So this is the setup that you can be able to come up with we can have, let's say this is the first chamber. In this chamber we can be able to have what we call the brine. The brine is actually also referred to as sodium chloride, which is concentrated, and the brine can come from trona, which actually gets obtained from salty lakes like Lake Magadi. Good. And when the trona is here, the trona can descend to something else here, and in this case we can have something called ammoniated brine. Great. We can have something else getting introduced into this same chamber that is what we call ammoniated brine, and this can be ammonia. This brine, I've told you, is actually concentrated sodium chloride. Good. So the brine is concentrated sodium chloride. Then we have NH3, 1 nitrogen and 3 hydrogen atoms, actually getting to that point of being bonded strongly by a type of bond called a covalent bond. Why is it a covalent bond? Because all these two are nonmetals, so they have that aspect of sharing electrons equally. I've said is actually ammonia. Great. After I'm done with that part, I can have another arrow from this end heading to this point. I can have another box here. Great. And in this box, I can be able to actually contain all whatever I want to say in this part. If this is a pot or a box, I can be able to put here brine saturated with ammonia. Brine saturated with ammonia. The brine now saturated with ammonia can come to this end. And in this end can have something called Solvay tower. Great. I'll have something of this sort here. I'll explain to you what it is actually. So the Solvay tower is here with all those things, just to actually make them longer for you to be able to understand. So the Solvay tower with all those extensions, they have their own role. If I'm done with that part, I can be able to come here and draw another chamber down here. So the Solvay tower can end up actually joining us here. And whatever we may have here is ammonium chloride. Okay, and maybe something else you can actually be able to extract from this is what we call sodium hydrogen carbonate. Great. And look at this. That means in this Solvay tower we have two products. I'll explain in detail how they actually come about. So we have ammonium chloride and sodium hydrogen carbonate. They are all coming from the Solvay tower. Good. And this Solvay tower is also sometimes referred to as a carbonator. So you can call it a Solvay tower or a carbonator. They all mean the same thing. A Solvay tower or a carbonator. Okay, and maybe to proceed from here, we can have coke at this point. Let me just put it here. We can have the coke here. The coke can also have something else, let's say limestone. So we have coke and limestone, coke and limestone, coke and limestone. So the coke and limestone are here. These two are actually taken into another chamber here that I can call a kiln or even a furnace that has very high temperatures. For example, in the extraction of iron, we always have what we call a furnace that is 30 meters high and lined with the steel to the outside and fire bricks made of magnesium oxide to the inside to maintain the temperatures inside the furnace that can now facilitate the extraction of zinc from its oxide. So here we have a kiln or furnace that has very high temperatures. Now, fortunately, whatever comes out of this can be, for example, CO2, and everybody knows CO2 is carbon dioxide. The CO2 can get taken into what we call the Solvay tower or the carbonator. Very good. Okay, and what else comes out of this? We can have something else like, let's say, calcium oxide. Calcium oxide is also called quicklime, and it gets used by agriculturalists to actually reduce the acidity of the soil. And in this case, you can be able to actually increase the yields on the farm, just in case the crops you are growing can work well under basic environment. So if I'm done with this part, I can have the calcium oxide getting taken into a chamber that I can purposely call a slacker, and a slacker will obviously have water getting introduced into it. Good. And whatever comes out can obviously be a very important product called calcium hydroxide. Good. And this is also called slaked lime. Slaked lime. So the coke or the limestone will be taken to the kiln or furnace under very high temperatures. Whatever happens here is called thermal decomposition. After thermal decomposition has taken place, the carbon dioxide gets taken to the Solvay tower or the carbonator. Solvay tower or the carbonator. Then the calcium oxide gets taken to the slacker. In the slacker, water is actually introduced into that slacker. The calcium oxide will obviously dissolve in the water to form slaked lime or calcium hydroxide. So the slacker coming from what it actually forms, the slaked lime or calcium hydroxide. Now, fortunately, what happens is that the calcium hydroxide ends up actually meeting with this region, you see, and on meeting there, we can be able to actually call this as ammonia regenerating chamber. Ammonia regenerating chamber, and the ammonia regenerating chamber actually regenerates ammonia. So more ammonia can get introduced here into that region of the ammoniated brine. So ammonia regenerating chamber giving us more ammonia, that gets added onto this part. What else comes out of this ammonia generating chamber? We have what we call calcium chloride, also gets produced from the ammonia generating chamber. So the calcium hydroxide meets with ammonium chloride in the ammonia generating chamber to form ammonia and calcium chloride. Water is also produced, and when water gets produced, the water will actually aim at ensuring that it gets to that point of also getting introduced into the slacker. Good. Also gets introduced into the slacker, or if not in the slacker, the water can also get introduced. So here we have water as also a product getting introduced into the slacker, and more water can as well get added. Or you can have as well this water also getting directed into the carbonator. So water again into the carbonator. Very good. Water into the carbonator. You can as well also have just more water again getting introduced into the Solvay tower from an external source. Good. Maybe from a river. That's why this industry can get located closer to a water body, so that water can get to that point of being used in this setup. So that is it, and I may want first to actually look at what I can be able to get out of this point. I left this point without further actually discussing it. This sodium hydrogen carbonate that comes from the Solvay tower can get introduced into what you call a kiln or a roaster, where roasting takes place. And in the roaster, what gets produced when sodium hydrogen carbonate undergoes roasting? We can produce carbon 4 oxide, you see, that gets recycled. Good. We can produce water that gets added into the slacker, so more water. Good. And we can have now our final product, which is actually sodium carbonate. Sodium carbonate. Now we can be able to actually write some chemical equations and more explanations for us to understand how this process aims at manufacturing. I've told you this process is called Solvay process. Its main aim is to manufacture sodium carbonate. So apart from getting sodium carbonate from Trona, from Lake Magadi, you can as well come up with sodium carbonate from the Solvay process. And this is actually a flowchart of how that process looks like. But I'm going to be very descriptive and very brief in as far as explaining this process is concerned. So let's begin from this point. So we have Trona. The Trona can be a very good source of brine. I've told you brine is concentrated sodium chloride. When the brine is here, it can get introduced into this ammoniacal chamber or ammoniating chamber. This chamber is called ammoniacal chamber or ammoniating chamber. So you can call this ammoniacal chamber. Why do we call it ammoniacal or ammoniating chamber? It is because this is where the brine gets ammoniated. The brine ends up having ammonia getting added onto it. So the ammonia gets added onto brine, so the brine becomes ammoniated. That's why we call this one ammoniated brine, or you can as well also call it ammoniacal brine. So you can also call this ammoniacal brine. Ammoniacal brine. So you can also call it ammoniacal brine. So the brine can get obtained from Trona. Okay? The brine, I've told, is concentrated sodium chloride. It gets added onto this chamber. The ammonia, for example, we can say The ammonia can get obtained from the Haber process. A Haber process is a process where nitrogen and hydrogen are combined under a temperature of 450 degrees Celsius and a pressure of 200 to 500 atmospheres in the presence of a finely divided catalyst. So in the Haber process, ammonia gets formed. The ammonia gets introduced into this chamber. Apart from the recycled ammonia as well, we majorly get ammonia from the Haber process. The ammonia gets added onto the brine from trona into this ammoniacal chamber or ammoniated chamber. What do we form? Ammoniated brine or ammoniacal brine. So a chemical equation to represent that stage, we have ammonia from the Haber process, good, combining with sodium chloride from trona to form what you call sodium chloride ammonia. Look at that. This is the one I'm calling ammoniated brine. Ammoniated or ammoniacal brine. The brine gets ammoniated. The brine ends up having ammonia getting added onto it. So it gets called ammoniated or ammoniacal brine. This process takes place in the ammoniating chamber or ammoniacal chamber. After I'm done with that part, of course, this is a gas. This can be aqueous. Of course, this is a complex compound, which can be a solid. Actually, an aqueous solution, for that matter. Okay, that is the first thing you're supposed to take note of. After we are done with that part, now we have ammoniated or ammoniacal brine. You can come here. So we have ammoniated or ammoniacal brine. The ammoniated or ammoniacal brine, which is actually NaCl.NH3, good, ammoniated or ammoniacal brine, it rises into this other chamber, and this way we have what we call brine saturated with ammonia. Now the one we are calling ammoniated brine or ammoniacal brine. So the brine saturated with ammonia. The brine saturated with ammonia gets introduced into this chamber. This brine saturated with ammonia further actually gets introduced into the Solvay tower. This Solvay tower is also referred to as the carbonator. This is where the brine saturated with ammonia reacts with water, for example, from a water body, like a lake or a river. So the brine saturated with ammonia is combined with water from a water body. Look at that. Then with carbon dioxide, for example, with carbon dioxide from the kiln, where the decomposition of limestone or calcium carbonate occurs. So carbon dioxide can get obtained from the decomposition of limestone. Limestone is actually calcium carbonate. It gets introduced into the kiln. It undergoes thermal dissociation or decomposition to form carbon dioxide as one of the products. The carbon dioxide gets introduced into the Solvay tower. Look at that. Then again from the roaster, we introduce sodium hydrogen carbonate. When the sodium hydrogen carbonate gets introduced into this chamber, we have what we call sodium hydrogen carbonate. The sodium hydrogen carbonate getting introduced into the roaster allows itself to undergo dissociation by use of what we call the excess heat. This also introduces more carbon dioxide. The dioxide of carbon is actually taken into the Solvay tower. So three things are actually getting introduced here. We have the water from the water body. We have what we call brine saturated with ammonia. Then we have what we call carbon dioxide from the kiln where limestone gets decomposed, or from the roaster where bicarbonate of soda or baking soda undergoes dissociation or decomposition. So we can write a chemical equation for that. We can say ammoniacal brine plus water plus carbon dioxide are able to combine to form sodium hydrogen carbonate and ammonium chloride. Good. So ammoniated brine is combined with water, is combined again with carbon dioxide to form sodium hydrogen carbonate and ammonium chloride. This process takes place in the Solvay tower or carbonator, and in this case the ammoniated brine consists of ammonia and sodium chloride or rock salt, and in this case water gets added. I've told you water can get obtained from a water body. Then the ammoniated brine comes from this other end. The carbon dioxide can come from the kiln where limestone gets dissociated, or the carbon dioxide can come from the roaster where sodium hydrogen carbonate undergoes decomposition. So in this case we'll end up having this as our products, and in that manner we'll end up having something of this sort. And of course the question is balanced, if I'm not wrong. One nitrogen, 3 hydrogen atoms plus 2, that is actually giving you 5. Then we have 1 plus 4, that is 5. We have 1 sodium, 1 chlorine, 1 chlorine. How many oxygen atoms? 3. Then 1 carbon. The equation is balanced. Good. So we are done with having sodium hydrogen carbonate and ammonium chloride. Good. Something to note. I actually introduced these lines here to show how the Solvay tower or the carbonator has what you call shelves. So the carbonator or the Solvay tower is shelved. It is actually shelved to slow down the movement of the ammoniated brine, so allowing more time for the reaction to take place, allowing more time for the ammoniated brine to combine with water and carbon dioxide. Good. So this actually slows down the movement of the ammoniated brine, and this aids in ensuring that the reaction occurs completely, so more sodium hydrogen carbonate and ammonium chloride are able to get formed. If I'm done with that part, I can as well move to something else. Now if you look at this, you'll realize that now 2 things are coming out of this. We have what we call ammonium chloride, that is NH4Cl. Okay, then what else also comes out of the carbonator of the Solvay tower? The sodium hydrogen carbonate. Good. Those are the products I've actually shown you here. So ammonium chloride and sodium hydrogen carbonate. Ammonium chloride and sodium hydrogen carbonate as the 2 main products. After we are done with that part, you have sodium hydrogen carbonate here. The sodium hydrogen carbonate gets taken to the roaster. Sodium hydrogen carbonate is also called baking soda or bicarbonate of soda. The sodium hydrogen carbonate is able to get taken to the roaster. In the roaster, the temperatures are very high. That is to say, the sodium hydrogen carbonate undergoes what we call thermal decomposition. And on undergoing thermal decomposition, it is able to give us 3 different products. So we have the sodium hydrogen carbonate undergoing what you call thermal decomposition. Good. And in that process, we will form sodium carbonate plus carbon dioxide plus water. Listen very carefully. Metal hydrogen carbonates of group 1 elements are affected by heat, but metal carbonates of group 1 elements are not affected by heat. That is to say, sodium hydrogen carbonate can get affected by heat to form sodium carbonate, carbon dioxide and water. This can be a solid, this can be aqueous, this can be a gas, this can be a liquid. And now depending on the temperature, this can be actually a gas as well. Why? Because when the temperatures are very high, it will form sodium carbonate as the solid or an aqueous solution. It will form carbon dioxide as a gas, and the water that gets formed easily turns into vapor. because of the excess heat. So this can be either an aqueous solution or as well a solid, depending on the prevailing temperatures. Now, before you can allow the sodium hydrogen carbonate to descend to this other end, where we have what we call the roaster, what happens in the Solvay tower after these two have been formed is what we call filtration. So one is soluble, the other one is insoluble. So if you look at this case, you'll find that sodium hydrogen carbonate is denser than ammonium chloride. So on being denser, it is easier for it to actually descend to this other end. Then the ammonium chloride remains at this point. Okay, so that means they have a different level of solubility. They get separated by a process called filtration. So for you to actually separate these two, there's a process I'm referring to as filtration. So the sodium hydrogen carbonate is separated from ammonium chloride by filtration. The sodium hydrogen carbonate or the baking soda gets taken to the roaster. In the roaster, the temperatures are very high. Thermal decomposition takes place to form sodium carbonate or soda ash or washing soda. Carbon dioxide is actually also produced. It gets recycled. It gets taken to the Solvay tower. Then the water also gets produced. The water can get taken to the slacker, where further reactions can occur. Okay, so if I'm done with that part, you should also look at this point. The ammonium chloride has actually been removed. It gets taken to what we call the ammonia regenerating chamber. Good. In this region, what do we have? You should note this. Limestone or calcium carbonate is taken to the kiln. In the kiln or furnace, the temperatures are very high. What happens? The calcium carbonate or limestone, also marble chips or chalk, undergoes what we call thermal decomposition. So the calcium carbonate undergoes thermal decomposition by what we call the excess heat to form quicklime or calcium oxide and carbon dioxide. Good. It's a solid. This is a gas. Look at that. So the calcium oxide is also called quicklime. Carbon dioxide gets recycled. Look at this. So the limestone into the kiln or furnace, what gets produced? Carbon dioxide. So the carbon dioxide gets recycled or gets taken to the Solvay tower. Now from the kiln, where the calcium carbonate has undergone dissociation, carbon dioxide gets taken into the Solvay tower. Good. And remember, to even speed up the reaction in the Solvay tower or carbonator, the brine is actually moving downwards, while the carbon dioxide is actually able to get moved upwards. So the ammoniated brine is actually able to meet the upward moving carbon dioxide. This speeds up the reaction to produce more ammonium chloride and sodium hydrogen carbonate. So here we have had a chance of getting carbon dioxide that gets recycled, and as well we have had a chance of getting calcium oxide or quicklime that gets taken into the slacker. Very good. Calcium oxide that gets taken into the slacker and carbon dioxide that gets recycled into the Solvay tower. Into the Solvay tower or carbonator. Good. Carbon dioxide, it is here into the Solvay tower carbonator. Then calcium oxide into the slacker, where we have what we call quicklime. Great. So what happens in the slacker? In the slacker, the calcium oxide meets with water from either the ammoniating chamber, where ammonia gets regenerated, or from an external source like a water body, like a lake or a river. So what do we have actually here? We have the calcium oxide combining with water to give calcium hydroxide, which is also called slaked lime. So you have what you call a solid, you have what you call a liquid, and then an aqueous solution. I've told you metal hydrogen carbonates of group 1 elements like sodium and potassium hydrogen carbonate get affected by heat. Because sodium and potassium are group 1 elements, the metal hydrogen carbonates of group 1 elements are actually affected by heat. They dissociate to form metal carbonate, carbon dioxide, and water. But metal carbonates like sodium carbonate and potassium carbonate are metal carbonates of group 1 elements. They don't get affected by heat. Okay, so even further heating cannot dissociate sodium carbonate. Why? Because metal carbonates of group 1 elements are not affected by heat. So any further heating does not further dissociate our soda ash or washing soda. Now I'm done with that part, and if I just go to this other end, now I'm actually able to produce calcium hydroxide. You see? So the slacker has calcium oxide and water. These two will give us calcium hydroxide as per this equation. Calcium oxide from this end, then water from this end. From an external source, they produce calcium hydroxide or select lime, which is calcium hydroxide, select lime. This calcium hydroxide is taken to the ammonia regenerating chamber. In the ammonia regenerating chamber, the calcium hydroxide is going to meet with ammonium chloride. Good. So the ammonium chloride from the Solvay tower carbonator will meet calcium hydroxide from this other end. What do we form? So we have calcium hydroxide and ammonium chloride reacting to form calcium chloride plus ammonia gas plus water. Good. So the calcium hydroxide, which is aqueous, reacts with ammonium chloride, which is aqueous, to form calcium chloride, which is aqueous, plus ammonia gas plus water, which is a liquid. Look at that. So in this case, I've had a chance of getting to that point of knowing how these products are able to get formed. So in that manner, we can be able to put 2 here, because you have 2 chloride atoms and you have 1 here. It means they are supposed to be 2. 2 nitrogen I can put here 2. Good. So 2 nitrogen atoms, 2 nitrogen atoms. Then there are 8. Then they are 2. So 8 plus 2. So 2 hydrogen atoms here, 5 hydrogen atoms here. There are 10. I'm supposed to put here 2. So that 2 times 3 is 6. 6 plus 4, that is 10. 2 oxygen atoms. 2 oxygen atoms. Great. Okay, so let's go back to the chart. From this end, we have water getting produced. Look at that, the first product. Okay, and then here we have what we call ammonia getting also produced. That is actually called ammonia regenerating chamber. So ammonia gets regenerated. It gets taken to this ammoniacal chamber. Ammonia is here. Then we have what we call calcium chloride, which is actually the only waste product as far as the Solvay process is concerned. The only waste product. Calcium chloride. Ammonia regenerating chamber produces calcium chloride, which is a waste product for this, but it's actually very useful. For example, calcium chloride that is actually taken as a waste product in this Solvay process